Okay, let's get started. So far, what we discussed is the amplitude modulation and the frequency modulation, right? So for the last 8 or 9 weeks, we learned a lot about the modulation, right? The modulation and also demodulation at the receiver. But what we always assumed so far was there's no noise. So whatever you transmit over the air, ST, right? That is received by the receiver, right? Because in the air, in the channel, we have no noise, we have nothing. So it's a perfect channel. We transmit something and we receive exactly the same thing. Okay, that's what we assumed so far. And given the channel is perfect, right? We learned how to do amplitude modulation, how to do the frequency modulation, and all those things. And also how to recover the amplitude modulated signal, also frequency modulated signal. Right? That's what we learned so far. And what we're going to discuss from now and onwards is noise. Okay? So no longer the channel is perfect. So our channel actually is not perfect. So we always have a noise. Right? So far, we're still talking about analog communication. We never talked about digital yet. Right? So probably next week, we're going to talk about digital communication. But still, we are talking about analog communication. But now the difference is that now we want to introduce noise in the channel. So simply speaking, this is our model. ST is the transmitted signal, right? And RT is a received signal by the receiver. Earlier, ST was same as RT because there was no noise, right? There's nothing in the noise. We always assume perfect channel. But from now on, what we discuss is ST is what we transmitted. And after we transmit, in the channel, we have a noise. So noise is added. This is noise. WT is noise. Noise is added to the transmitted signal. That is what we receive. So received signal actually is equals to, okay, received signal equal to transmitted signal plus noise. Okay, that's the model we always assume from now and onwards. We call this kind of noise as additive noise because we are adding it, right? Adding the noise. So we call that as additive noise. Okay, additive because we are adding it, right? So that's what we are going to assume. That's what we're going to model it. In this case, okay, the most important thing is what is this noise? That's the most important thing. We need to know the statistics of the noise. Generally, noise is random. Okay, you cannot find out what exactly is noise at any instant time. At any instant time, the noise is random, completely random. We can never know what the value is because it's completely random. But what we know is that we know the statistics. We can find out what is the average of the noise, average power of the noise, or what is the statistics, what is the value, what is the statistics of the value of the noise. Only those things we know. Okay? So that is very important to know the statistics of the noise. When you have this kind of model, we have this kind of things. So first of all, what we need to do is that we need to minimize the effect of the noise. Why is that? Because this is our transmit signal. Okay? So perfect channel is we have no noise. That's perfect channel. But we have a noise. So if noise is big, right? If noise is really big, then we are not going to receive the correct symbol. Okay? We cannot recover our signal. So therefore, if possible, we need to minimize the impact of the noise. We need to minimize the impact. Okay, that's a prime concern. That's the most important thing. We need to minimize the effect of noise. That's the most important thing. Okay, but as I said, we don't know exactly the instantaneous value of the noise. Only thing we know is the statistical value. not the instantaneous value. So eventually what we are going to do is we need to find out the ratio of the signal power versus the noise power. That's what we call as a SNR, signal to noise ratio. Okay, so we're going to talk about signal to noise ratio many times throughout this course. Okay, so that's the most important thing. You probably want to remember the word SNR, signal to noise ratio. Okay. We learned amplitude modulation, right? And in the amplitude modulation, we learned the coherent detector and also non-coherent receiver. So what was the non-coherent receiver we learned? We learned the non-coherent receiver. We also learned the coherent receiver for amplitude modulation. Okay, so what was the non-coherent receiver? Envelope detector. So what does that mean? Coherent receiver means that you need to match the phase and then you recover the signal. That was the case of Costas receiver and also coherent detector. Costas receiver eventually wants to find out the phase and you want to correct the phase, right? So Costas receiver is still coherent detector. But a non-coherent detector is something like an envelope detector. Think about envelope detector. Envelope detector basically works and you don't need to know the phase. Okay, envelope detector works just based on the envelope detection. It is nothing to do with the phase. You don't need to know the phase, right? So that's a non-coherent detector. So amplitude modulation can be detected or can be recovered. The message can be recovered by two different ways. You can use a coherent detector at the receiver, or you can use a non-coherent detector at the receiver, like an envelope detector. Okay, there are two different ways. Generally, the non-coherent detector, like an envelope detector, has a little bit worse performance. Coherent detector gives you better performance, generally, right? So Costas receiver gives you better performance. That's a better receiver. Envelope detector is a very simple one, so that's the advantage of using envelope detector. The performance is not good. Okay? So we have those two things. But still, the amplitude modulation, amplitude modulation is not a very good modulation, especially when you have a noise. Okay, because a noise is being added. So if you transmit like 1 volt, and noise is like a -2, for example, then eventually what you receive is -1, right? So especially when you have a noise, amplitude modulated signal, amplitude modulation is not a very good modulation compared to the frequency modulation. In this frequency modulation, your message is not in the amplitude, right? Your message is in the frequency. So even though you have a noise added here, your frequency component is not much affected. So that's why generally the frequency modulation is a better modulation, especially when you have a noise. Okay, we'll talk about that later. Let's look at here. Frequency modulation. You can take a look at the red sentence here. Frequency modulation allows us to trade bandwidth for improved performance. What that means is, think about the frequency modulation. We learned the frequency modulation, right? When you use a frequency modulation, if the message signal has a single frequency, okay, message has a single frequency, but still the frequency modulated signal has a very wide bandwidth, right? So you use very wide bandwidth. Okay, you use a very wide bandwidth, but what do you get? Using wide bandwidth is not a good one, right? We always use a small bandwidth. What we want is to use small bandwidth. That's what we want. But in FM, you need to use a wide bandwidth. That's not good, right? But still, there's something you can get. What do you get? You can get improved performance, especially when you have noise. Okay, the performance is very good in FM. So that's why it says a trade. So trade-off. You are losing some bandwidth because you need to use a wide bandwidth, right? So you need to you are kind of that's a bad side. You are using wide bandwidth, but what is a good part? You have a very good performance. So if you use a smaller bandwidth, now then the performance is going to be decreased. If you use large bandwidth, performance increase. So somehow you can trade off. You know what trade-off means, right? One is good, then the other is bad. Something like that. That's trade-off. So bandwidth and improved performance, that's kind of trade-off. If you use a wide bandwidth, performance is good. If you use a lower bandwidth, the performance is a little bit worse. Something like that. That's possible in FM. In AM, that's not possible, right? Because you cannot change the bandwidth, right? In amplitude modulation, your signal is in the amplitude, and your amplitude will be affected by the noise. Okay, so there's nothing like you can trade off, but in FM you can do trade off between bandwidth and improved performance. In the later slide, we'll talk about these things. There is a pre-emphasis and de-emphasis filtering. So, okay, and in order to reduce the noise, we'll talk about that in the next slide. So this slide basically talk about some basic knowledge about the noise. So you need to have some basic knowledge about the noise. Okay. So in order to talk about the noise, we need to also discuss about random process or random variable. So here we have some random variable. And when you talk about the noise, we always look at this equation. So let me talk about a little bit on this equation. First, I need to ask you a question. You probably heard about AWGN. Did you hear about that? AWGN? What does that stand for? Additive white Gaussian noise. That's AWGN. So now let's take a look one by one. Additive means our noise is added to the transmit signal. That's additive. Okay, so that's simple. Gaussian basically means that when you have a noise, let's take a look at the noise in time domain. Let's say this is time, and you are receiving noise. In that case, the received noise is something like this, right? This is like a noise. Okay. Sometimes you get some big value. Sometimes you get a small minus value. Sometimes positive. Sometimes negative. Okay. Your value changes every time. Every second you get a different value. Okay. You get a noise. So this is a time domain. But when you look at that, let's say in the sample domain, or we call that as ensemble domain. Okay. In that case, what we're going to draw is that we're going to look at the probability density. So what that means is here's a 0. Okay. So if you get a sample value 0, then you have here. And let's say this value, let's say is a +1. In that case, you have a +1 here. You have a -1. So this statistics in this domain looks like a Gaussian. That's what they mean. Okay. So what it means is when you get a noise and you measure the noise for a long time, okay, and you keep measuring all these things, right? And then let's say you get let's say million samples, all noise, but million noise samples, and then put noise samples and plot here. Think of it this way. You get a million noise samples, right? Sometimes you get noise value +1. Sometimes you get -0.5. Something like that, right? You have a million samples. Now, what you want to do is that you want to draw a histogram of those million samples. What is a histogram? Histogram is a graph. But this graph shows you how how often each sample appears in the whole measurements. So for example, we have 1,000,000 samples, noise samples. And out of these 1,000,000 samples, how many times do you get 0? Maybe this much, maybe this much. And how many times did you get the sample value 0.1? Maybe this much. Maybe you get a sample value 0, maybe 1,000 times, and 0.1, maybe 900 times, something like that, right? And out of these 1,000,000 samples, you get only 100 samples with the value +1. Something like that, right? That's a histogram. So if you have this kind of histogram, something like that, and you are adding all this value, like 1,000 samples in 0, 900 samples in 0.1, something like this, right? So you are adding 1,000 plus 900 plus, you are adding all these samples, the total number of samples will be 1,000,000, right? So you get 1,000,000 samples, and the first sample, you may have a value -1. Second sample, maybe the value is 0.1, something like that, right? Then you count how many samples do you get 0.1, and how many samples you get +1, okay? Something like that, and you count number of samples for each value, then you make a bar graph like this. That's a histogram, right? 1,000 samples. So 1,000 samples, I mean 0, when you measure the 1,000,000 samples, 1,000 samples out of this 1,000,000 will have a value 0. Okay, that's what they mean. So when you draw a histogram of these noise samples, that will give you some kind of distribution. That distribution shows you Gaussian. And what I'm talking about here is the same thing, actually. So this is a histogram, but this is a PDF, the density, probability density function, but these two are same thing. Okay, same thing. Because this one you can change into PDF, right? Because we measured the 1,000,000 samples, and out of these 1,000,000 samples, 1,000 samples are in here. So what is the probability that your sample, your random variable goes into the value 0? What is the probability? It's something like 0.01, simply speaking. And here, same thing, like 900 divided by 1,000,000, something like that. So you end up getting a Gaussian. Same here, right? So this value here, maybe you get this value sometimes here. Sometimes you get this value here. So when you keep measuring the noise samples, then you're gonna, and then you keep getting the noise samples and you measure the PDF, then you're going to get this kind of PDF. Do you understand what I'm saying here? PDF? So our noise has, if you look at the noise sample, then noise sample will give you Gaussian noise. Noise sample will give you Gaussian distribution. So that's what they mean as a Gaussian. And this is just noise, right? And we know that this is additive noise. So that's why we call the additive Gaussian noise. Now the one last thing is this is a white noise, right? Why do we call that? Why do we call this one as a white noise? Noise never have a color, right? Why do we call it as white? Why not red? Why not black? Why white? Yeah, we discussed that, right? Think about the prism. Yeah, the white color is a mixture of all different colors with the same equal power. So when you look at white, okay, white, you always need to think about the frequency domain. It's all frequency domain. So let's look at the frequency here. So this is a frequency domain. We have a 0 here, something like that. And our noise is a white noise. So therefore, when you look at the noise power distribution in frequency domain, the noise power is distributed equally for all frequencies. Okay? All frequencies you have equal power. This is what they mean as white. Okay? Now think about that. You have a prism. What is a prism? You have a white light, and the prism will dissolve it, will make it all different colors, right? Each color is a different frequency. So each color is a different frequency, right? Right? And when you look at the prism, if the incoming light is perfectly white, then the output color spectrum has all equal power distribution. It's all equal power for each color. So yellow color, same power, red color, same power, blue, all different color has the same equal power, like this. All different frequencies has equal power. Only then this original one becomes white. If you think about some different color distribution, different power distribution like this, it's not equal, for example. In that case, when you combine all together, the original light is not white. Maybe red color is a little bit stronger than the other color. Then this is a little bit reddish white, not perfect white. So perfect white means that you have exactly equal power distribution over the whole frequency. That's the white. So our noise has this distribution. This is power distribution, power. So we call that as a power. We call this as a power spectral density, because what we are plotting is a power. Okay, power. This is power, and we are plotting this one in frequency domain. So that's why we call this spectral and density. So this is a power spectral density of our noise. Okay. So what you can see from this power spectral density is that which frequency has which amount of power. That's what you can find out. So in this case, every single frequency, all the frequency has equal power, because this power spectral density is equal, flat, right? This is the condition of white. Okay? And our noise has this condition. This is our noise. So what does that mean? Our noise has an equal power distribution over all the frequency. So what does that mean? That means nothing to us, right? I don't know what that means. Okay, so in order to understand this, what we need to understand is the relationship between, let me call this one as, we need to know the relationship between the power spectral density and we need to know the relationship between these two. Okay, this is a power spectral density, and power spectral density has a very, very close relationship with the autocorrelation function. What is autocorrelation? We learned the correlation before, right? What was the difference between the correlation and convolution? General convolution. Let's go back and let's say hx equals to fx and gx. So fx is convoluted with the gx, and the output is hx. So this is a convolution, general convolution. F and g convolution, we get h, right? So that is a general relationship. What's the difference between this convolution and autocorrelation? In autocorrelation, it means auto. It is about correlation, but it is auto correlation. So auto basically means itself, right? So you are not doing convolution with another one. You are doing convolution with your own. So it's like fx convoluted with its own. But on the second one, we put the minus. Remember that? Why is that? Yeah, because in general, in convolution, you first flip, right? And then slide in convolution, right? In general. But what you want to do is you want to find out the correlation with your own because it's auto. So you are convoluting with your own, but let's say your fx looks like this, and then if you're doing convolution like with your own, then this one looks like this. And when you do the convolution, the second one you are going to flip. So if you flipped it left to right, then it's going to be like this, and then slide. Okay? In that case, this one and this one is like a left to right. This is not. It doesn't match, right? Because it's a flipped. In that case, it's not exactly correlation. So that's why what you want to do is you want to take a minus x. In that case, this one is originally this one. Because we took the minus, we flip it again. Now you want to do convolution, so you are going to flip this. Okay? Once you flip this, then this one looks like same as this. When you do the convolution, you're going to flip it, so you're going to have the same shape, and then slide. That way, you basically slide with the exactly same function, so therefore you can calculate the correlation, autocorrelation, right? So the difference between autocorrelation and convolution is that since this is autocorrelation, you are doing convolution with your own, but not just exactly one, but you put the minus. So that way, this is autocorrelation. But what I'm asking is, what's the relationship between these two? Simply speaking, power spectral density is a frequency domain, right? As I showed you earlier in the graph, like this. This is a power spectral density. Okay? What you can see from the power spectral density is that how much power is distributed in the frequency domain. So this is a frequency domain. Autocorrelation function, this is time domain. And when you look at here, this is a power spectral density. So power. So generally power is amplitude square, right? So this is a power spectral density. So this is power. In autocorrelation function, this one is also square. Why is that? Because you are multiplying your own. You multiply this one with your own, right? So this is going to be square. So autocorrelation, every correlation function is going to be square. You are doing convolution with your own, right? So when you slide, let's say this one matches exactly like that. When you slide, sometimes it match, right? If it match exactly, then it's going to be square. Exactly, right? That's the time you get a peak. When do you get a peak? This one matches exactly, you get a peak. Okay? So this autocorrelation function is generally a square in time domain. This is a power, so it's going to be square in frequency. This is a power, this is a square in time. So what's the relationship between these two? These two are simple Fourier transform relationship. You take a Fourier transform, you get this, time to frequency. Same way, inverse Fourier transform, you can change power spectral density back to the autocorrelation function. So these two are simple Fourier transform relationship, just time and frequency. In the earlier, when you learn the Fourier transform, okay, Fourier transform, you probably didn't learn about power. Okay, you always learn like some amplitude or some signal in time domain, right? Some time domain signal, not the autocorrelation, just time domain signal. Take a Fourier transform, then you're gonna get frequency response. That's not power, right? So that was the relationship. Some time domain signal, time domain response. Take a Fourier transform, you're gonna get frequency response. And again, inverse Fourier transform, come back to the time domain response. Right? So that was what happened. And here, it's actually same. The only difference is that in this case, in both sides, in time domain, frequency domain, it's square. Because it's power, this is autocorrelation, so these are square. Both one. Okay? But these two have the Fourier transform relationship. Okay? Yeah. So now let's come back to this white condition. This is a condition of white in spectrum. So our noise has this kind of power spectral density. That's why we call this noise, our noise is white. Okay? Our noise is white because our noise has this power spectral density. Now then, let's take an inverse Fourier transform of this power spectral density in order to get autocorrelation. Okay? As I said, power spectral density and autocorrelation, this is a Fourier transform relationship. So if we have this power spectral density, now then you want to take an inverse Fourier transform of this one, you're going to get autocorrelation function of our noise. Right? So let's take an inverse Fourier transform of this. What is the inverse Fourier transform of that? Let's say in frequency domain you have this graph. And let's take an inverse Fourier transform. What do you get? In frequency domain, flat. So in time domain, you're going to get delta function. That's the relationship of a Fourier transform, right? So in time domain, you're going to get delta. Because in frequency domain, we have this, right? Inverse Fourier transform. In time domain, we get this. Then what is this? Our frequency domain is the power spectral density. So therefore, in time domain, what we have is autocorrelation function. So this is our autocorrelation function. Autocorrelation. So this is our autocorrelation function. Okay? What does that mean? Your autocorrelation function is delta. So what does it mean? Yeah. Generally, right? Generally, in general, autocorrelation function goes like this, goes up slowly, goes up with a certain slope, and then get a peak, and then goes down. That's typically what the autocorrelation function looks like. Okay? Autocorrelation function generally goes up with a certain slope, and then get a max, and then goes back down like that. Right? That's typically what autocorrelation function looks like. But in this case, it's 0, and suddenly peak, and then again 0. Okay? That's autocorrelation. So what that basically means, let's think about a autocorrelation of fx as an example. Let's take a autocorrelation, and our fx looks like this. Okay, like that. And let's take autocorrelation. Then we are doing convolution of these two, and fx looks like this, and f minus x looks like that. So let's do convolution of between these two. Then doing convolution, let's flip this. Then it's going to look like same. And you're going to slide. Okay, when you slide. Initially, when you slide like that, then there's no overlap. So it's going to be 0. And this one keep moving. And then it goes here, then we have a little bit of overlap. So you're going to goes up like that. And keep moving. And we have a more and more overlap. And eventually you have a perfect overlap. Matches exactly. That's the time you get a peak. Right? And keep moving. Then you are moving out like that. So again, your overlap region is getting smaller because you move out, right? So it's coming back down. And eventually when this one completely passes, then there's an overlap, so it becomes 0. So that's why autocorrelation function typically looks like this, right? But now in our noise, we have this autocorrelation function, and we have 0 all the time, and only when we have a perfect match, we have a value. Otherwise, we get all 0. What does it mean? What that basically means is our noise is like this. We have our noise. Let's say here's a noise. And we are doing autocorrelation. And our noise is like when we have even overlap, still the correlation is 0. Correlation is perfectly 0, and only when you have a perfect match, you get a peak, and you have a little bit of offset, little bit of mismatch, you still get 0. That's what they mean. Only when your signal noise is perfectly matched, you get some value. So let me throw it here. Let's say our noise is W2, okay? And our noise looks like this. This is our noise as an example, okay? And what we're going to do is we want to do autocorrelation of our noise. So since you are doing autocorrelation, we basically make another copy of this and doing correlation, right? And let's draw this one same way here. Since this is autocorrelation, let's say same thing, okay? And then when you have here we have this much of the offset. So in this case, the autocorrelation is 0. And this one keep moving. And now we start to have overlap. Like that. We have overlap, but still 0. Correlation is 0. And you have a little bit of overlap, a little bit of mismatch. So maybe 90% are overlapped. 90% is overlapped. And only a little bit of mismatch. Okay? But still 0. Correlation between these two is still 0. Do you see what I'm saying? Only when this one is perfectly matched, this one in time domain, it's perfectly matched, then you get some value, and then keep moving. And you have a little bit of mismatch, again it go back down to 0. That's our noise. Okay, that's the noise. So our noise, simply speaking, our noise is very special noise that you have a no correlation with the adjacent sample. That's what they mean. If you have a little bit of sample mismatch, the correlation is 0. That's our noise. Why do we have such things? Because our noise is white noise. So when you look at the white, okay? When you look at white, first thing to remember is this power spectral density. Why? Because white means equal power distribution in frequency domain. That's what white means. So when you look at the white, first thing to remember is this picture. Okay, power spectral density. And what this picture power spectral density means, this power spectral density eventually means that our autocorrelation of this noise looks like this. Okay? Our noise has this autocorrelation. because our noise has this power spectral density, our noise has this autocorrelation, right? And if we have this autocorrelation, what does that mean? That means our noise has this kind of thing. If you have a little bit of mismatch, your correlation is 0. So what that means is this. Let's say you have a noise coming in. This is noise. Okay, that's noise. Let's say you get this sample, noise sample. Let's have you have this noise sample, and then next noise sample. Okay, so you are talking about two different noise samples, but that's this is sample 1, this is sample 2. So it's a next sample. What's the correlation between these two samples? 0. That's what they mean, right? Even though these two samples are very close, okay? This sample, let's say in time domain, the time difference between these two samples, let's say it's 1 nanosecond. Just example, right? These two samples, noise samples, are very, very close. What's the correlation? 0. That's our noise. So in our noise, simply speaking, no correlation. No correlation between other samples. If you have a little bit of time mismatch, correlation is perfectly 0. That's our noise. Why? Because our noise is white noise. Okay? So you need to remember these things. It's very important. Okay? Very important. Everyone probably heard about AWGN, but you need to understand this whole thing. Okay? That's the exact meaning of white. We have this power spectral density, we have this autocorrelation, so therefore we have this relationship. The samples between noise samples, between the two different noise samples, always correlation is 0. Always. So the equation you are looking at here is the relationship, is the autocorrelation function. So this is autocorrelation function. Your autocorrelation is going to be delta at tau equal to 0. This one, right? 0 here. That's autocorrelation. So that's what you mean here. That is our autocorrelation. And what is this one? This is a power spectral density. And our power spectral density in frequency domain, this is F, right? The power spectral density has constant value. Why is that? Because it's flat here. And what's the value of here? What's the value? This is a power value, right? That is, we call this n naught over 2. We call this one as n naught. Why? It's n nothing. You can call it n0, but in English, they call this n nothing. 0 means nothing, right? N nothing, but people just call it as n naught. N naught. Okay? So a lot of people call this one as n naught. N naught. So this particular value here is n naught over 2. So what is n naught? Noise power. We call the noise power as n naught. And this n naught is one side noise power. So another way. So this is a frequency domain. If you think about only one side, this one actually has a positive side, a negative side, right? You have a positive value here, negative value. So if you think about only positive area, you can think about this kind of noise power spectral density. This is again power spectral density, but this is one side. This one is a power spectral density for both sides, right? Both sides, but this is one side. When you look at this one side power spectral density, this particular value is going to be n naught. But when you look at this one in the both domain, both sides, and you need to keep the same power, so this n naught is now divided into 2. So that's why the level goes down to n naught over 2. Okay? This one and this one, same thing. Basically same thing. But whenever you see the power, noise power, you will always see this value, N naught. So just whenever you see this N naught, okay, remember that, okay, we are looking at the noise power. This is noise power. And typically when you look at the noise power, you're going to see the N naught divided by 2. Why? Because of this picture. The level here in both sides, power spectral density, this power is N naught over 2. Because N naught is defined by one side power spectral density. And since you are looking at the both sides, right, the level here is going to be N naught over 2. Okay? So this is going to be, this is our power spectral density. That's this one. Since this is a flat, this is a constant, right? So this is a constant. That this equation, this picture, same thing, right? Same thing. And that picture in autocorrelation, this picture, same. And what was the relationship between autocorrelation and power spectral density? This is a Fourier transform relationship. So this equation here in time domain, this relationship in this one in power spectral density, this one and this one, these two are Fourier transform relationship. Okay, so yeah, that's what you need to remember. This is a Fourier transform relationship, and our noise is a white noise. Therefore, you have a flat power spectral density, and take an inverse Fourier transform. Now you are going to get this impulse autocorrelation function. Therefore, in our noise, you have a no correlation between the two different samples. That's a conclusion about our noise. Okay? Yeah. So remember this whole thing and this equation, that equation. That is our noise. Simply speaking, right? Noise is random. So if you have, let's say, this is time domain, and we want to measure the noise, and then incoming noise is like that. Let's say this is noise. Since noise is random, you never know what is going to be the value. You cannot expect each noise sample. So as I said, we have this kind of relationship, and our noise is white. What that means is, let's say you measure this noise sample, okay, and you measure this noise, and this value was +1. Then, since you received the noise and noise value was +1, can you expect what's going to be the next noise sample? No, right? Because each one is completely not correlated. Okay, so therefore, when you look at this sample, okay, you can never expect the next sample because it's completely random. And there's no correlation between samples. That's our noise. So what does it mean is we cannot do anything about the noise sample. Because every time it's random, there's no correlation. So there's nothing we can do about the noise. You can never expect. You can never estimate about the noise. However, what you can see is that you can find out the noise power. You can find out the noise power. How do you know the noise power? Since you are getting noise samples, okay, each one is a sample. Like this one is plus 0.3, this one is a minus 0.2. So you are keep getting this kind of noise sample. So how do you measure the power? Just square. Okay, each of these samples you get million different samples, and then square and take an average. Then probably you are getting some kind of noise power like this, right? That's going to be noise power. You can measure the noise power. That's the only thing you can get. And you also knows that our noise has a Gaussian. So that's the statistics of our noise. And we can measure the noise power. So these two are the only information you know about the noise. Okay? You can never know the exact sample value. You never know. But you only know our noise is Gaussian statistically and noise power. That's the only thing you know. So based on that, we can try our best. So that's the whole thing about this slide. So let's move on here. In here, okay, what you're seeing here is, again, ST is what we transmitted signal. And here is, you can see NT. NT is a noise, okay, noise. So it's edited. It's being added into noise. And XT is received signal. But when you compare this equation with the previous equation that I showed you, this one, something is different, right? We still have ST, the transmitted signal. But in this slide, we say that our noise is WT. But on the next slide, we say NT. So what's the difference between the WT and NT? The NT, it says narrowband noise, NT. Going back, this WT is just additive noise. So there is some difference between those two. Okay, here's the difference. Earlier, we said that our noise is a white noise, right? So therefore, we have this spectrum, power spectral density. Okay, so throughout the whole frequency, we have an equal power. But in general, in our system, we are only using our bandwidth, right? We are not going to use the whole frequency. We are going to use only our own bandwidth. So maybe the bandwidth for you, maybe is this one. This is your bandwidth. Okay? All the other frequency is for someone else. Right? So your system will only take this much bandwidth. So therefore, even though the whole thing is a noise, in your system, you're going to receive only this frequency. All the other frequency, you are not going to receive. Because that frequency is for someone else. You are only going to receive this much. So the noise power for your bandwidth is going to be NT. Noise for the whole band, WT. That's the difference between the two different noise. That's why we call, in this case, WT is the noise over the channel, the whole frequency. However, when you look at our own signal, okay, we are only talking about the noise in our band. So that's why we call this a narrow band noise, and we are writing as NT. We'll talk about that in the next slide. Okay, going next slide, you'll probably understand a little bit better. And when you have this signal, XT, that's received signal, transmitted signal, and this is noise. Okay, when you have this signal, you receive XT. What is important? The most important thing is this one. This is the most important thing. Most important thing. SNR stands for signal to noise ratio. Signal to noise ratio. Okay, signal to noise ratio. This is actually very easy to understand. Okay, very easy. Let me explain this way. Let's say I'm transmitter and he's receiver. Okay, I'm transmitter, he's receiver. So I'm basically talking to him. Okay, if there's no noise, then I just talk and he just listen. But let's say suddenly he came in and he is making noise. Okay? In that case, for him, I'm talking, but he's also talking. But what he's talking about is a noise to him. In that case, what's the performance for him? The performance is going to be, from his point of view, my voice versus his voice. If he speak loud, okay, then this is noise, his voice. This is my voice, right? My message, this is his message. If the noise, what he's talking is much louder than what I'm saying, then noise power is much large. So in SNR, if the noise power is large, then SNR is low. Okay? Putting another way, he's making noise, but I'm speaking loud. In that case, ST has a big power. So therefore, this is a signal power. This is signal power. This is a noise power. Okay? So that's why we call this signal power, signal power versus noise power ratio. This is ratio. So this is a relative value, relative. Okay? If the ST is large, signal power is large, and then if the noise power is the same, but signal power is large, then SNR is big, right? SNR is large. Okay, so when you have a noise, the system performance is based on this signal to noise ratio. Everything is based on the signal to noise ratio. Okay, so that's why this is the most important thing, and not only here, but every time when you look at the communication system or signal circuit design, and everywhere you will see noise. Think about circuit design. You have a noise, right? Over the circuit, there is a noise. So therefore, you will see signal to noise ratio there also. In communication system, there is also noise. Everywhere you see noise, you will see signal to noise ratio. So this concept, signal to noise ratio, you will see it everywhere, okay, everywhere. So very important. Okay, so okay, let's continue next time.